Hello, this video is all about forming differential equations, first order differential equations. Quite often we've got some sort of natural phenomena we're investigating, and the first thing we need to do is create an equation. Quite often they create exponential growth or decay, but sometimes they're simpler than that. For example, if I fire a rocket up into the atmosphere, well, it's being pulled back by a constant force, gravity. So that's a simpler one. But sometimes we've got like the temperature of the water in a kettle. Once it's boiled, it starts to lose its temperature, doesn't it? And it starts to drop back to the temperature in the room. So that's a sort of decay. Radioactive decay is another one, isn't it? We have a certain number of nuclei and they decay over time. Or in finance, we might have invested some money and we might want to see it increase, and it usually increases in proportional with its original value over time. So first thing we do need to do in forming these differential equations is understand this term rate of change, because that's what we're going to use. Here's some examples of rates of change. Velocity is the rate of change of displacement. What does that mean? It means it's the change in displacement over a short period of time. Yeah, and we know that v equals dx by dt. So velocity is the rate of change of displacement with time, with respect to time. Acceleration is the rate of change of velocity. So it's the amount of the change in velocity over a short period of time. Population growth, well, that rate is, well, it's the rate of change in the population, so it's a change in population over a particular period of time. And if I had an investment, the growth rate on that investment will be the change in its value over a short period of time. So as you'll have seen, everyone in this column here, these rates of change are differentials, aren't they? Whatever my variable is, dt, because it's the change in that variable over a short period of time. In fact, it's over an instant in time, and we are looking therefore at the differential. So let's look at turning expressions, statements into equations. Let's have a look at this. This is probably the simplest form. So the rocket's going up into space and it's being pulled back by gravity. So I'm going to do F equals ma vertically. So what have I got? Well, I've got a negative force, mg, because it's going down, and that's going to equal ma. So A equals negative g. So that'd be my starting position. A equals negative g, but I know that A is dv by dt, and that will equal negative g. So what have I done? I've written a differential equation. First order, because I've got a single, it's by dt, isn't it? It's the first differential. Let's have a look at some others. Temperature of the water in a kettle. So we boil it and it starts to lose heat. And the heat loss is, and its rate is proportional to the temperature difference, okay, between the water in the kettle and the ambient temperature in the room. So as we know, we boil the kettle, it goes up to that temperature, and then it starts to drop back, doesn't it? And actually, it will drop back to the temperature in the room. So let's have a look at what that means as an equation. Well, the rate of heat loss, so that's dt, big T for temperature, by dt, little t for time, is proportional to the difference in temperature, T minus TA. It's also negative because it's reducing, and I think it's really important to be thinking about signs here because they have meaning. Okay, but that's a proportional relationship and we need to turn it into an equation. So what do? We add our constant of proportionality, and hey presto, I've now got a differential equation. D big T by dt equals minus k lots of T minus TA. Radioactive decay. So if I've got a number of nuclei, n, then the rate at which the decay takes place, i.e. the number of lost nuclei in a period of time, instantly, is going to be dn by dt. and that's proportional to the number of nuclei we've got, and it's negative because it's decaying, isn't it? So again, I've got a proportional relationship, so I write that first, and then I'm going to turn it into an equation by adding my constant of proportionality. So there's another differential equation. Let's have a look at another one we use a lot, investment. So if I've got some investment, financial investment V, then anytime its growth rate is proportional, growth is proportional to its value. A growth rate, by which we mean rate of change, is going to be dV by dt, and that's proportional to its value. So if that's a proportional relationship, I want to turn it into an equation. So I have my constant of proportionality, and my sign is positive because it's going up, and that's why I've made a point of putting it in there. Yeah, it's not decaying, it's not depreciating, it's increasing in value. So there you are. That's my summary of the first piece of our thinking. So first thing we do is create a word equation. Then we convert it usually into some sort of proportional relationship, making sure to be clear where our rate of change is. That's going to be our differential. Once we've done that, then we usually convert it into an equation by adding our constant of proportionality. And I think it's really important to have the sign here, because it's going to tell you whether we're in increasing or decreasing period of time, of value rather. Okay, so there you are. Note that down, and we'll pick up how to solve them in the next video.